Okay, g'day all, welcome to another video. So today we're going to talk about AES key expansion. And we're going to implement the ending to our AES implementation where we expand the keys and finish up the encryption side of things. So to begin with, the key is supplied to the algorithm, and what we want to do today is mostly perform a bunch of operations to expand that key into 10 different keys. Actually, I think there's 11. Yeah, including the original key. So that's what we're doing today. We're expanding our key. Page down doesn't work. Alrighty, so AES and 128-bit keys. What we want to do is create 10 new keys. Each of them is 16 bits wide or 128 bits. And this is what it's going to look like in the end. So first of all, we'll have our original key. And after that, we'll have the key for the first round and the key for the second round, all the way up to the key for the 10th round. Down here. So in total what we need is 176 bytes for our expanded key. Page down does work. Alright, so the key expansion algorithm itself is one of the more fiddly parts of AES. I mean, it's just as difficult as the mix columns step, which was just awkward. So this is kind of how it's broken down. We've got a key expansion core which has 3 steps: rotate, SBox and archon. And we sort of repeat that over and over again a lot in the middle of our key expansion algorithm. The key expansion core takes 4 bytes from the keys that we've generated so far, and what we end up doing is XORing those 4 bytes while we go. We'll see all of this in just a little while. I'm seriously confused about big endian versus little endian here, more so than I should be, but I think it's big endian. So we view the 4 bytes like this: byte 0, byte 1, byte 2, byte 3. And byte 0 is the first, byte 3 is the last. Yeah, I don't know if that's big endian or not, but it's the opposite to the way that you'd normally view an integer in x86. Okay, so the key expansion core. The first thing that we want to do is define a new function called key expansion core. It's going to take an unsigned character array of 4 bytes long, although we don't sort of specify 4 bytes anywhere. I'm just going to use a pointer. And it also takes an archon iteration index. We'll get to that in just a second. So if we come over here to our code and see where we were up to. So our code at the top has a bunch of lookup tables. And if we scroll down a bit, we'll see all of these other functions that we wrote last time. And our little main method. Okay, so find your key expansion function, and just above that you want to define the key expansion core. I'll actually just copy the code since I've already typed it out 300 times. Probably not that many. Alright, there it is, key expansion core. Okay, so the rotate left instruction is pretty basic. We just treat the 4 bytes that are passed to the core as a single entity, and we rotate them left. So the 62 just here, this is just an example here. If we had 12, 62, 54 and 126 in our 4 bytes, the 62 would be moved over here to position 0, the 54 would become position 1, the 126 would be moved to position 2, this is 0 based counting, and the 12 just here would be shifted out on the left and it would pop back in on the right. Yeah, so it's just like a shift operation, but rotate, the bits come back in on the other side. Okay, so I'm sure you can think of a lot of different ways to do that. Here's 2 just here. You could use either. I might go for this top one just here. I think an optimizing compiler will realize that this code just here is just a rotate, and yeah, I think the Microsoft compiler is pretty clever. It'll figure that out and do something much like this code just here. Anyway, that's the rotate left. So you'll notice that I'm rotating right just here. Yeah, that's because the integers are stored in the opposite way. So yeah, I don't know. If that's confusing to you just there, then just copy this code down here and maybe it'll make more sense. Alrighty, but the SBox step, the next step of the key expansion core is an SBox lookup. So we've spoken about the SBox before. It's this substitution box, and if you want you can go to Wikipedia Rindale SBox page and just copy that. But if you've been following along, you should have the SBox already, so I'll just copy this code just here and explain it. Alright, so each of the bytes that we're passed to our key expansion core is replaced by whatever its corresponding value is in the S box. So if I scroll up the top, just to remind us where our S box is, there it is just there. Yeah, just a 256 byte lookup table, the S box. So in 0 becomes whatever the S box value at in 0 is, in 1 becomes the S box value for in 1, yeah, etc, etc. Nice and easy. So we've done that thing before. We've done S box swapping before. Alright, and the Archon step, the final step of the core is the Archon step. I can't remember what that stands for, Archon. I don't know. It sounds like an 80s space shoot 'em up. Does it? We raise 2 to the power of I minus 1, remembering that I is the Archon iteration number. And then we add this to the value of the first byte in the group of 4. So what we're doing here is saying that the first byte of the key expansion core becomes itself plus 2 to the power of I minus 1. Now, this is Galois fields. So the raising of this power just here is not normal arithmetic. It's that weird Galois field arithmetic, which we've been through before. And the addition just here is XOR. Yeah, so it's Galois field arithmetic. We've been through it before, so I don't want to look at it again. But good news for us, this Archon step just becomes another table lookup. Yeah, fair enough. Fair enough. Alright, so if we go to Rindale key schedule, let me just see if I can bring up my, well, obviously can't. It's here. If you go to Wikipedia, the Rindale key schedule page, you scroll down to about 1/3 from the top, 2/3 from the bottom, you'll find it just here, unsigned char Archon. Just another table lookup. So we want to copy that. I mean, you could type it out. You can actually compute this as well if you want. It would be a waste of time though. And we want to add that table to the top of our file where there's lots and lots of tables. If I thought about this a bit more, I'd split these tables into different files over here and make things a bit neater, but yeah, I think it's good how it is. Just all in one file. So we've got our Archon table. You want to put a semicolon on the end of that if you're using C++ like I am. And the first byte is XORed or added to whatever the Archon substitution is for I. Yeah. It's interesting, but if you think about it, the I parameter won't be any of those 256 values. The I value will only be, I think, the first 10 or 11. Yeah, so we don't actually need this entire table. But anyway, this is Archon. And that, my friends, is the key expansion core. Click to add a title. Okay. Let's not. I thought I turned off spell check too. What the? Alright, but moving right along, so the key expansion algorithm itself relies on that key expansion core. The first thing that we've got to do is copy 128 bits to the first 16 bytes of our expanded key. So I think in the code I've actually... That's here, yeah. So the function at the moment doesn't even take any parameters. I don't remember what I was thinking, but well, let's just copy this to here. And explain ourselves. So the key expansion step takes an input key, that's the first 16 bytes, that's the original key. The first 16 bytes of our expanded keys is the same as that original key. So the first thing that we've got to do is just copy those over. Yeah, just like that. Just using a little for loop. Of course you could use, you know, integers, pointers if you want, or like Q word pointers and copy that faster, but we're not talking about optimization here. Okay, so the next thing that we've got to do, we need a few variables. We've got to keep track of the bytes generated so far because we're going to want to know when we've generated all 176 bytes of our expanded keys. We're going to want to keep track of the Archon iteration value, which for us is going to start at 1. And we also want a temporary storage place for calling the expansion core. So those are those variables just there. Let's copy those over to the code. I might just mark this as variables. Whoops. What have I done? Here we go. I found it again. It's all good. I say, go away. Okay. Bytes generated so far is set to 16 because we've already generated the first 16 bytes by copying our original key. That's good. Alrighty, so the main loop of the key expansion is this. While bytes generated is less than 176. So in other words, while we've still got bytes to generate. Let me just copy this. Okay, while we've still got bytes to generate, what we want to do is read the previously generated 4 bytes. That's the last 4 bytes that we've generated, and store those in this TMP array, TEMP array, sorry, temporary array. So this is what we're going to call the core with. You can do that little storage just there with this for loop just here. So for I equals 0 to 4, and read the previously generated 4 bytes with I plus bytes generated minus 4. Alright, let's just copy that. Okay, so that's going to read 4 bytes into our TEMP array. And the next thing that we want to do is, once every time we've got to generate a new key, we've got to perform the core with temp as a parameter, those 4 bytes that we just copied, and the current archon iteration index. So the archon iteration index at the start will be 1, but it's going to count up as we generate new keys. So the thing is, once every 16 bytes, that's once every new key, yeah, we want to call this key expansion core. So well, that's what this step here is. Only when bytes generated mod 16 equals 0, we want to do this. Yeah. Watch it too, I put the plus plus over here on the side. You could actually do this if you want. I think this is probably easier to read. Yeah, it doesn't make a difference. It doesn't make a difference. Okay, so that takes care of performing the core. XOR and store. Okay, so the other thing that we've got to do, once we've got our 4 bytes generated from the core, we've got to XOR temp, whatever the core returned to us, with 16 bytes previous to the ones that we generated. So these are the bytes generated so far, just here, these blue ones and these yellow ones. What we want to do is XOR the first 4 bytes with the temp value, and then store that as the next 4 generated bytes. Now, I hope that makes a bit of sense. So at the start, when we've only got 16 bytes, which are the original key, there won't be any of these red bytes just here. Yeah, it'll just be these 16 just here. Okay, anyway, that's what we've got to do next. So I hope I've got code. Yes, yes I do. Alright, so this is the code just here. XOR temp with bytes generated minus 16. And store in the expanded keys as the new key. Or as 4 bytes of the new key. Let's pop that down there. Okay, so that's the end. That's the end. Yeah, let's just come back to our code for a second. Let me just zoom out for a bit. That is the key expansion. Yeah, just there. That's going to take your 16 bytes and expand it to 176 bytes. Yeah. Alright, but we're not finished. We're not finished because we actually have to use those bytes now to encrypt something. So let's finish up AES encrypt. If we go back to our code, this function just here. So this is where we actually perform the encryption. At the moment, it's wrong, but we'll fix it. Let's finish AES encrypt with our new keys! Exclamation point. I must have been excited. Here's how we left it last time. Jolly good. Okay, so firstly, the number of rounds is 9 for AES 128. So AES 128 requires 10 rounds, but the final round down here is a little bit different, so we do that separately. The number of rounds that we perform in our loop is 9. So we'll pop a 9 there in number of rounds. The next step is to expand the key to 176 bytes. Now, I've actually gone about this a stupid way, and I didn't realize until the end, but you should expand the key outside of AES encrypt. Yeah, expand it once and then reuse the expanded keys. That's not what I've done, so my implementation just here will be very slow. Yeah, you'd expand the keys outside of this method here and then reuse them, because they're going to be the same expanded keys throughout your document that you're encrypting. Okay, so let me just copy this code here to our program. So we define a character array of 176 bytes. We pass in our original key and key expansion, that method that we just spent 14 years composing, just up here, is going to expand that into heaps of really good things. Okay, so now we've got to use our expanded keys for the add round key steps. So instead of using our original key, which is the way that it does it at the moment in the code, we want to use our expanded keys. So that's this line just down here. Oh, I didn't copy the A. Better remember. Okay, so the key for each round is 16 bytes of expanded key. And yeah, this is how you compute that just here. So expanded key is just a pointer. I mean, they call it an array, but there's no difference. Expanded key plus 16 multiplied by the round index. Yeah, and the round index is actually base 1 counting instead of base 0. So I had to add on that 1 just there because my for loop counts in base 0. I'm sure there's clearer ways to do this, but I hope that makes some sense. It doesn't mean anything to me. Okay, so that's the add round key for the middle of our algorithm, but we can't forget that we've also got to add the round key for the final round. Yeah, so expanded keys plus 160 is the final round's key. So instead of using key just here, which is the original key, we want to use expanded keys plus 160. Yeah, so every 16 bytes in expanded key, there's a new round key. And yeah, that's what we're using for our add round key. I hope that makes sense. It's so difficult to know if what I'm saying makes any sense at all, but that's kind of what we're doing. Okay, so the other thing that we want to do is actually return the encrypted message instead of returning the normal message, or instead of not changing the message at all. Now, there's a bunch of different ways that you could do this. I've decided to just copy over the original message with whatever the state is. So the state throughout this algorithm so far has been the message as it's encrypted, and at the end we want to copy that encrypted version over the top of the message. Now, you mightn't want to do that because you lose the original message, but I don't know, maybe you do. I don't know. Oh yeah. Sorry, I might just tab all this stuff across. Okay, so this is copy over the message with the encrypted message. Exclamation point for int I equals 0, while I is less than 16 I plus plus. And message I equals state I. Look at that. Look at that. That's fantastic. Okay, so we're getting somewhere now. Alrighty, so what we've got now will encrypt 16 bytes of a message. So if we were to pass this message just here, as we have it in our main method, and this key just here, AES encrypt will only encrypt the first 16 bytes. What we actually want it to do is encrypt the whole message. So let's have a bit of a look at how we do that. In order to use AES 128, what you've got to do is pad your message to 16 bytes with zeros. So if your message isn't 16 bytes wide, and it generally won't be, you want to add zeros to the left. To the left? Yeah, to the left of your string just here. So let's have a bit of a look at how to do that. Here it is just here. This is padding and copying the message around to a slightly larger string padded with zeros. So let me just paste this down here and talk through it. So original len is the length of the message, Message up here is a null terminated string. So it's actually like this, secretly in memory, but don't tell anyone. It's null terminated, and strlen just here will figure out where that null is, and it'll report that as the string length. Len of padded message begins as the same as the original length, but what we've got to do is figure out how to round that up to the nearest multiple of 16. So that's what this if statement just here does. If the length of the padded message is 16, I mean if the original message was 16 bytes already, or something divisible by 16, then we don't have to add any extra padding. But if it's not 16, then we want to do this obscure looking thing. Which means round the length of the padded message up to the nearest 16 byte boundary. I'm not sure that I did that right. I wonder what happens if your message is 0 in length. Yeah, there might be a bug in this program just here. There might be more than one of them. Anyway, the next step is to copy the original message to our padded message, but wherever the original message has nothing, so yeah, this might be, say, I don't know, 3 times 16 bytes wide, and we might have to add a bunch of zeros at the end like this, just to make it all add up to a multiple of 16. So wherever we're outside of this message just here, well, we want to add zeros. So that's this line just here. If I is greater than the original message, then put a 0 there. Otherwise, copy the byte from the original message. So all of this just copies the original message to our padded message and pads with zeros if it needs to. The next trick is to encrypt the padded message by passing blocks of 16 bytes through our AES encrypt. So let me just copy this, and I think something's going very strange with this copying here. Could you? But that doesn't look like it copied it. I'll have a look. Let's see. I did. Sneaky. Sneaky. Okay, so encrypt the padded message. What we want to do is run through the entire length of our padded message, jumping in blocks of 16 bytes. We're talking about a block cipher here, so we're jumping up in blocks of 16 bytes. We're calling AES encrypt with padded message plus I, so whatever this offset pointer is here. Yeah, we want to encrypt blocks in padded message of 16 bytes in size. Now, this right here is where I pass the key, okay? So this is where I hang my head in shame at my own stupidity, right? So instead of passing the key just there and expanding it in AES encrypt, what I should have done is expanded the key out here, like key expansion, right? So that we've got our expanded key right here. That's how you spell it as well. And then we could just reuse that each time instead of expanding it in the AES encrypt method. Anyway, I won't say anything if you don't say anything, and we'll pretend that it's a really fast implementation of AES. So that is how we encrypt our padded message and how we pad a message, etc., etc. I think the final thing that we should do, and this is really quite important, we want to know if the results that we've encrypted are correct. So that's the final step down here is to, and delete padded message as well. The final step down here is to print out the encrypted message in hexadecimal, just like this. So print out a little heading, encrypted message, and then print out each of the bytes in hex. So my print hex function just here. You can just turn C out. You can use hex, or sorry, you can use C out to print hex, but I didn't like the formatting of it. It doesn't pad it with zeros. So I wrote my own little print hex method just here. Yeah, so we should be right as rain. If I just take away that breakpoint just there and hit run, we should actually have an encrypted message. Let me get rid of these zeros first of all. Hit run. It's time to cross your fingers, folks. Boy, that was quick. I think I saw that though. Let's actually add a getch down here. Despite everybody complaining when I use get. H. You could add you know, whatever method you want to prevent the window from closing. You're supposed to be able to go up here and say I don't know, something like I don't know, something like Shift F5 is meant to not close the window, but when you're debugging, it doesn't work for me. Here we go. We've got ourselves an encrypted message. So let's just scroll up. This message will be encrypted with will encrypt. This is a message we will encrypt with AES. I can't even read. That message becomes this set of hexadecimal, and if we've done things right, if AES works, this set of hexadecimal digits is pretty difficult to reverse and get this message back without having this key just here. Okay, but if we come over here to whatever this thing is called, and we go to google.com, and we go to AES Encryption Online, and we open up a couple of these sites. So I think these first two here are really good. Okay, that's good. So this is a test site, and we assume that this is correct. We assume that this is correct. So if we come back to our code and we copy our message into the test site as a text, that's right. Electronic code book is right. We don't want plain text. We want hex. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I might just change the key to. No, I won't. I'll use the keys. We'll use the same key. So 01, 02, 03, 04, 05, 06, 07, 08, 09, A, B, C, D, E, F, and 16. Alright, so those are the hex digits for those. Yeah, I should have just gone with an easier key, but what we really want to see here is does the website encrypt exactly the same? Okay, so we've got B6, B4, 27, BB, B6, B4, 27, BB. Okay, does it end with OE83D1? OE83D1. There you go, my friends. So that is AES encryption. We have encrypted a message with AES. And this website just here, which is aes.online-domain-tools.com, is an excellent place to test your AES. It's got a couple of different modes too, which I haven't been through. And you can also encrypt with a plain key, a plain text key. And you can encrypt hex messages as well, if you like. So that's very cool. This website just here is pretty good as well. It's simpler though. But yeah, not bad. Actually, I don't think that is the one that I wanted to show you. I think it was maybe this one. Oh, that's not it either. Well, there was another really good website for testing your AES encryption. I'll see if I can find it. It was very, very good. No, it's not that one either. I've been to all of these at different times. This was it just here. See, I like this site just here. Yeah, I like this site just here. This is testprotect.com-appendix or /appendix/AES calc. Yeah, so I reckon these two sites are very good for testing. But I mean, it's up to you. There's a lot of other sites that do this as well. Okay, let me just hit stop and see what else we've got to go through in the slides. Okay, problems and improvements. So I shouldn't have expanded the key for each block like I did. That was just a silly decision, but you know, it's all good. Hackers could read the byte in the S box after we've run our AES algorithm and potentially discover the last bytes that we read from the S box by timing the cache hits and misses. Extraordinary, but the implementation that we just did then is not recommended at all, and it's actually recommended that you don't implement your own AES because it's so difficult to do it in a way that's not crackable, not reversible. So people can do strange things like read bytes from the S box after we've done our AES to figure out which bytes our AES read from the S box. It's bizarre, but they can do that. Apparently, I can't imagine. Whatever. We didn't save the length of the original message anywhere, nor did we save the length of the encrypted string. So these sorts of things would have to be added. I mean, if you're going to encrypt a string like this, and you're going to come up with some list of random bytes. It's not null terminated or anything, so you know, you should probably save a header or something at the start of your encrypted message, which specifies the original length of the string so that you have some sort of clue what's going on when you've encrypted it. Yeah, but that sort of thing is up to you. You know, the actual implementation of the algorithm is entirely up to you. Oh, there we go. I had it in my slides anyway. So I recommend these two sites for testing your AES out. And that's it. We're done. So decryption follows much the same steps. It's reversed and you use different lookup tables, but it's basically the same sorts of tricks. So I think from what we've been through here in encryption, decryption shouldn't be too difficult for you to figure out. Don't use what we've programmed in any real applications. I've just put this up for interest because like I wanted to know how the algorithm worked and I wanted to share with people how it works. If you ask me, I don't see why it's that secure. Do you know? I really don't. I really don't. I mean, I am not a hacker. I hate that sort of programming, but I don't see why this is not reversible. But that's just me. That's just me. Okay, so well, that's about it, really. Oh, the other thing that I should mention is that there's actually an AES instruction set in modern CPUs. So if you were doing this for production code, especially if it's going to run on x86 CPUs, you don't want to code the AES algorithm yourself because you won't be able to do it anywhere near as fast or securely as the hardware instruction set can. Maybe we'll look at that in the future in assembly, the AES instruction set. It's much easier to use, but it's still pretty confusing. Yeah, it's still pretty confusing. It's not just as simple as, calling AES encrypt or something like that. You've got to still expand the keys and that sort of thing, but yeah, we might look at that in the future. I don't know. But that's it. So I've got a Patreon and I've got a Facebook, I've got a music channel, and I've also got a Twitter, but I don't tweet very much. Maybe I'll start though. I might start tweeting something. You can sub if you're in the mood. You can like me on FB or just in your heart. I'll know if you like me in your heart. And that's about all that I wanted to do on AES. So next time I think we'll get back into doing more varied topics. This has been a very difficult series to get through, particularly because it's so narrowed, it's so narrow. Anyway, it's been really, really interesting. I hope that video helps people to understand how the key expansion step works and the general flow of AES. Yeah, I want you to have a really brilliant day. See you all later.